Okay, thanks, Aaron, for getting us set up.
For sure.
My name is Ian Mitchell. You can see it down in the little left-hand corner of your view of me. And our speaker today, like me, was trained as a computational scientist in traditional numerical solutions of partial differential equations. And at that point, all similarities completely end. Eldad graduated from UBC with a PhD in geophysics and seismology in 1998, and then worked at Schlumberger for a few years before rejoining academia and spending 9 years at Emory. And then he came back home to UBC in 2010 with an NSERC Industrial Research Chair in Computational Geoscience. And I couldn't quite figure out, Eldad, has that been transformed into a CRC chair since then?
We're finally done with it, which means that now I am free to do more or less what I want.
Right. And I was going to say, despite the title of your previous industrial research chair and your home in the Department of Earth, Ocean, and Atmospheric Sciences, nobody would describe the pace of Eldad's research efforts as geologic. This being a CAIDA seminar, I probably don't have to remind anybody that the best computational techniques used for modeling, predicting, and influencing the world have changed just a little bit since 2010. And over the past few years, Eldad has leapt into machine learning, not just leading the way for, or perhaps dragging traditionalist numerical differential equation research into this new world through his publications, workshops, and even a summer school last summer, but also publishing in top ML conferences like ICML and ICLR. Just this morning, I woke up to, in my email box, finding a link to an article in SciAm News entitled Deep Learning for COVID-19 Diagnosis, which described research, I think I understand, in which Eldad and his co-authors deployed a hyperbolic neural network, which is a new architecture drawing on ideas from hyperbolic PDEs, to efficiently train deep neural networks to spot signs of COVID lung damage in CT scans, despite the high variability of human-labeled training data and the massive size of these 3D imaging data sets. I don't think that material is in today's talk, so if you're interested in a recording of his presentation from the 2020 SciAm Conference on Mathematics of Data Science on this topic, it's apparently posted to SciAm's YouTube channel. So Eldad has authored or co-authored over 150 publications and has written various software packages that are widely adopted by industry. He co-founded two companies, Computational Geosciences Inc. in 2011 and Extract.ai in 2017. Before doing his PhD and probably before his undergraduate, he was a member of an elite combat unit in the Israeli Defense Force, and he regularly competes in marathons and triathlons, including the Swiss Man Extreme Triathlon, which is an Ironman length event that is just as grueling as it sounds. Those of you who have met him know that he brings the same kind of intensity and combativeness to his research efforts. So I have no doubt that Eldad will entertain us today with a controversial statement or three. He has also volunteered to take questions. So if during the talk you would like to call him out on his controversial statements, you can unmute and ask them, or post to the message board and I will ask them. So with that, I'll turn it over to Eldad.
Okay, so first, thank you for the introduction. I don't know if I can live to this kind of thing, but okay, I'll do my best here. So this work, let me talk a little bit about this work and how we kind of came to this. We did a lot of work on experimental design in geoscience and actually even in biology about 10 years ago. And then I was in the summer school last year, and Andrew Stewart was teaching about semi-supervised learning, and suddenly we realized that we can combine the two things, the things that he was doing and the things that we were doing, to come up with new ideas for active learning and things that people, for some reason in the active learning community, did not think about. And it's kind of how it kind of started. So it started a year ago, and we worked on it, and some results came, and there is a paper, I think, right now on arXiv, but let me maybe tell more about it as it comes. So here's what we're going to talk about. I'll try to do motivation and try to link it to whatever happens right now in the world a little bit. And then, as I said, it all came from talking to Andrew Stewart on semi-supervised learning and graphical methods. And so we're just going to do the background on the semi-supervised learning. From there, you'll just give the leap from the jump from semi-supervised to active learning, and we'll talk about some numerical solutions and examples. We'll talk about these two things. So let me go to the next. This is doing this one. Okay, so motivation. The problem is usually comes when you have to label some population, and it's difficult to populate it because you have insufficient resources. And a good example for this, which we are all facing right now, is the question of who should you test in order to diagnose people that may be sick with COVID-19. So as we know right now, this is one of the major bottlenecks in terms of opening the economy. And how do we test people in a smart way? And who should we test is really a big question that comes right now. And this is really not being addressed. I mean, although the techniques I'm talking about right now are kind of well known, for some reason, it's not really being deployed in the world right now. And people are not doing what we would call the obvious things in terms of doing these kind of things. And I'll get back to this maybe at the end of the conversation. So to kind of go to where we are with this, let me kind of look at the motivation and write a little bit more mathematically. So we have to assume a population that divided into two groups. And for this particular case, we can think about infected and susceptible. So people that have already got the disease and people that did not get the disease, for example. You can think about it as red dots and black dots. And of course, the problem is that you don't know who is who. And what you know is that you need to sample them. So you need to go ahead and label these things. So right now they're all white because I know nothing about them. And I need to label them somehow. So now I can decide that I'm going to label a few of them. So here I labeled, in this case, 2 of them. And after I label them, I can say, given the fact that I know these 2, can I find out what the rest are? Can I find out in any way that, how can I find what are the rest? And I can run some code, and I can find out that here are the rest ones. So the ones that are, I noted here as red, are the ones that I actually sample. And the other ones, hopefully you guys can see my screen, are the ones that I deduced from these ones that are red. And hopefully I've done a good job, and it depends. I mean, I can screw it up. Like probably, by the way, almost any algorithm will not do this point right, will probably get this point wrong, but it doesn't necessarily matter right now. I mean, so the point is that from these ones, I can go ahead and I can find out who is red and who is black, and I can make decisions based on this. So again, we know that we don't have to sample the whole population in order to understand who is infected and who is susceptible. I can sample only a part of the population and get from this. Now, let's write it a little bit more mathematically even. So I have a data set, X, which is made of, so capital X is a matrix, and each Xi here is a vector. And in the previous example that we have here, you can think about that each point X here have 2 coordinates, X1 and X2, which is the location in space. Of course, in the more complicated situation, X would be different features. So for example, if I want to think about labeling, I can think about X would be where you live. I can think about age. I can think about anything that comes into this vector that will give me some idea of what the data set is of a person. And I have associate labels. For each X, I have a label. And again, in the simple example of infected, not infected, can be that either infected or not infected. Okay? Or by the way, you can even put more, I like more the likelihood of being infected. I know all the X's, so I know the data, but I don't know the label. I don't know the Y. Of course, the goal is to compute an estimate of this Y, which we're going to call Y hat. And it's important to distinguish between Y hat and Y. Y hat is just an estimate, so clearly it's going to be wrong. Hopefully it's going to be sufficiently right, such that it's going to work for me very well. Now, I can assume I can sample the data. I can go ahead and sample from this X, but it's expensive. I mean, I have a finite budget. I can't go and say, let's sample everybody in the crowd. I can sample only a few people in the crowd. So, and I have a certain amount of budget to do this. And now the question comes, how should I sample the data and get the best estimate that I can have here? And you can think about it in a second in 2 ways. I mean, one is just getting the estimate. And the second thing, so far I did not talk at all about the model. In a second, I'll talk about the model that links X to Y. But we'll talk about this in a second. So that's kind of the first question. Okay, so if I'm looking at active learning, this is kind of the main goal of active learning, and you can think about two approaches here. One that are based on a generative model. So you're trying to find a model, in this case a function f of x and theta. Theta are going to be parameters, but they're going to predict a y. And the question would be, how would I find this? I mean, how would I'm going to calibrate this function by sampling points here? That's one approach here. So the idea would be I'm going to minimize over this theta, and I'm going to go ahead and find models to do this. So almost all the work, or the early work on active learning, was the idea that that's how you do. So you can think about a very simple thing. If you think about the simple regression, f is linear. So you think about capital X times theta is equal to y, and then you say, which ones should I sample? Which one of the things should I sample here? And these are very relatively simple models. There have been recent work, especially by Noach, who've done, there's actually an ICML workshop that if anybody is interested to know more, when he's talking about these things, that all these approaches are very useful for under-parameterized model. Linear regression is one of them, is a simple thing. But for over-parameterized model, we're talking deep learning, for example, these methods fail quite miserably. And one of the reasons is because these, like deep learning, can basically fit anything. So it's very hard to, for example, in the previous approaches, what you would do, you would sample the function a little bit, see where you, because it was under-parameterized, see where you were screwing up, and then say, okay, I'm going to do more measurements to see where things are working for me. But in the over-parameterized models, you can fit basically anything. And this is why it's all these approaches that people used before really does not work. And only really relatively recent work, which is 2017, 18, 19, 20, people start working on these things and getting results that are different. So again, I mean, Noach, I think, have the most interesting theoretical treatment that I've seen on this particular thing, and it's worthwhile seeing. So again, these methods relates to the fact that you come with a model. Again, a deep neural network is a model that depends on parameters, and you say, let's try to train the model based on finite samples that I have. Okay. There is another approach, and the approach that we decided to take here. The approach we decided to take here is to separate things into two steps. The first step is we say, let's just estimate the data. So we're not going to train any model. We're not going to train a deep neural network or a subword vector machine or anything like that. All we're going to do is we're going to try to estimate the labels, given the few labels we have. The second thing we're going to do is we're going to take the labels we trained, and we're going to train them over the whatever technique you want to do. There are a number of advantages to this kind of approach. So first thing, as you'll see, the two steps are very tractable. So you're not really mixing the estimation method that you're trying to, the parametric method you're trying to estimate with how to estimate the labels itself. Both problems are very tractable and very relatively straightforward to do. The second thing is that over-parameterized method requires a lot of data. So if I have now y hat and it's relatively accurate, and we'll go and talk about that later, then you can train over-parameterized methods very well with these kind of things. And the last thing is that you can ensemble different models. So practically speaking, a lot of people have tried these things and know that this is working very well. I mean, you don't have to have only a single model. You don't have to have just deep network. I mean, I may have deep network and an SVM model. And after I have this data y hat, I can train whatever I want. And I can go ahead and say, let's try different models and see how they work for me. So once again, I mean, I'm going back right now to the dots, because maybe that will be the simple thing to do, is to say I have nothing. I'm going to sample first a few samples over here. All I'm going to do is take these samples, estimate the rest of them, and then I'm going to use all these data sets with the one that I know and the one that I estimated to train a deep network, which is different than saying I'm sampling this and I'm using only this to estimate, to train a deep network. That's the approach we're taking, which is quite different than most approaches you've seen in the literature on this thing. So hopefully I made myself clear, because now we're going into details on things, okay? And something here happened. My computer decided to close down. TechShop decided to close down. Sorry. Okay. Let me just leave it like this. Maybe that's better. Okay. So we were here. Okay. So first thing, let me just do another kind of now link to another field. It turns out when you look at this problem again, you can think about this. The problem is very similar to a sensor placement problem in experimental design. So let me go. I think I like the dots picture. I know some people maybe don't like them because they think they're too simplistic, but I really like this idea because to me they're very very simple and very revealing somehow. So let me go back for a second to these dots. You can think about it this way. Let's say I want to measure temperature. I want to know what the temperature is at every point here. The question is, where should I sense the temperature so I can get an accurate representation of everything? So you can think about it this way. I measure the temperature here, I measure the temperature here, and the rest I'm basically interpolating. I'm doing some fancy interpolation to find out, given the fact I know the temperature here and here, everywhere else. And then I'm going to use it. And so, by the way, the fact I'm finding the temperature doesn't mean I have a model for the temperature. I just know what it is. And later on, I'm going to maybe find out a model. I'm going to find a polynomial model or a more support vector machine or a radial basis function or a deep neural network. I don't care what it is. But the thing I'm doing is the first thing I'm just deciding I'm going to measure in two places. Now, which places I want to measure, so again, going back to here, which places I want to measure is the same as saying that I want to put a sensor over here and a sensor over here and not in any other point. And again, so this is the sensor placement problem, which have been solved in many, many different things. It's just that, again, typically when you think about sensor placement, you're putting sensors in 2D because that's where we can put things, and that really looks like that. In the machine learning world, each dot here can be in very high dimensions. So it's the same thing. It's just happening not in 2 dimensions, but in a much, much, much higher dimensions. But it's exactly the same problem. It's where do you want to measure in order to infer what's going to happen in the rest of the points? And that's kind of another link for something here. So we're here. Okay. So this is the sensor placement problem. And the sensor placement problem is really the thing that is being worked on in experimental design. Okay. So optimal experimental design is a very old field, and you can think about which experiment or which measurement should I take. That's kind of the field. Many, many papers for a very, very long time. It's a big field with books and everything else. I'm not even starting to quote the literature over here. But this is really where you should kind of should think about. And in this talk, what I'm going to do is I'm going to link the active learning to what people call optimal experimental design, which is really more of the bread and butter of experimental design in many different ways. And even in experimental design, the problem kind of can be more or less divided into problems that are overdetermined and underdetermined. The overdetermined would be kind of the old way of doing active learning. And the underdetermined problem would be overparameterized techniques. So I'm basically using the experimental design which was developed for overparameterized or underdetermined problems. And you'll see in a second. Okay. So let's go back to this whole thing. So now again, all I want to do is I'm not going to do the learning. All I'm thinking about is first step is how am I recovering all the labels, given a subset of the labels. That's the first thing I'm thinking. And I didn't say right now how to choose them. I'm assuming somebody gave me these labels. Or somebody decided or give me a few labeled points. And the question is, how am I going to find the rest of them? So here's the problem. I'm giving you a few points, data points, X and Y's. The Y's are labels. And the goal is to evaluate all of them. Okay? The mathematical model is very simple. It's a denoising model if you think about it. I'm giving data which is equal to Y plus epsilon, where when the small index I belongs to some set of measured points. And then the goal is to estimate all of Y. Okay? Clearly, the problem is ill-posed. It needs regularization or prior, depends on what kind of religion you are, Bayesian or frequentist. We'll talk about both religions in a second. We're equal opportunity offenders over here. And now you go ahead and you say you're off to the races to solve this problem. And we actually know quite a lot about solving these kind of problems. They're not new to us. So Uri taught me in this course long time ago. This is in 2 dimensions. So I need to make this maybe a little bit smaller. Ways to solve it, and it's based on, well, we used to call it in this case, it was based on the Laplacian, so smoothness. And in the data science world, we use a graph Laplacian. So what are we doing? I'm going to, for those of you who don't know graphs at all, I'm going to wave my hands very quickly on these things. The idea is that we take every point and we link it to whatever we call its neighbors in a very high dimensions. So we decide, for example, that this red point is related to these points, and this point relates to that point. And for that, what we have to have is we have a distance function that decides how close each point to each other. In the simplest way, you can think about an L2, but to be honest, L2 is not necessarily a good idea. In some cases, it works well. In others, it doesn't work well. And what you do is you basically write the graph Laplacian as being the exponent of this kind of function, and the I components is the sum of all the rest of them, or minus the sum of all the rest of them. And that gives you a function which is the graph Laplacian, a matrix which is the graph Laplacian, which you can think about as the extended, for those of you who comes from PDEs, you can think about it as something similar or almost identical to a discretization of the whatever 5-point Laplacian in space, or 7 points if you want to do, or sorry, 9 points if you want to do something in 2D, if you want to have more neighbors. But it's the same idea. Now, what's the idea behind all these methods? They say, look, I know this point is red, and I know this point is black. So if this point is close to this point, then clearly it should maybe get a red as well, because it's close to it. So if I know, you can think about it this way. If this patient is sick and this patient is close to him, both, for example, in proximity, in age, and everything else, well, then I should label this one as red as well. And if, on the other hand, this one is very far from our red point, then maybe it should be labeled as black. That's kind of the underlying thing. And by the way, we do it all the time when we do interpolation of data based on, in the PDE world, when we're actually want to try to go ahead and regularize and find out, for example, a temperature field. This is just an extension of all these kind of ideas. So here is the problem you're solving. You're presenting a minimization problem, and you're assuming the labels are smooth over this particular graph. And then what you do is you find out a solution such that this y transpose Ly, which is the quadratic form with the Laplacian, is small. Basically means this is smooth. What you want to do is you want to use a weighted least squares. And in a second, we'll talk more about this particular matrix W, where it looks like this. This is the y minus d. So remember, d now I'm going to give values that are the measured values of what I know at where the points that I know where they are. And I can give whatever I want somewhere else, because this w have zeros in places that I don't measure. So all I'm doing is I'm taking the data that I measure. I want to make the data misfit is small, and I want to take the regularization to be small as well. And that's a classical approach. Again, those of you who took Uri's course long time ago, he actually gave this example on a grid, and you would solve this and get an interpolation for something on the grid, and there's an analytic solution for this thing, which looks like that. Now, I want to maybe here say something for the machine learning people who want to use something else. And for example, you can think that if I have two classes, why am I using something like a softmax or basically a logistic regression? And I'm not saying you cannot use them. It's just that this set of this type of solution leads us to an analytic solution, which will be useful in 2 minutes from now. While if you're getting something like logistic regression, you're not getting an analytic solution. You get an optimization problem to solve, but without analytic solutions, and it's more difficult to apply whatever I'm going to talk about next. So this is one advantage of writing in this way. It may not be optimal from a machine learning point of view, but it does give very nice properties for the active learning point of view. Okay, so a few comments before we continue. So first thing, an appropriate distance function is crucial. For examples that are kind of cooked, it's very easy, or geometric kind of, when you look at the papers, it's kind of very nice to come with least squares. But these kind of D based on, for example, autoencoders or other things can be very useful with respect to the data. So what's the right distance function to use? I did not say, which means I'm escaping probably the most difficult problems that exist in this whole work. How do I determine that two things are actually close to each other? That's really one important thing. The second thing is that when you have a higher order, when you have data in high order, in high dimensions, you may require something more aggressive than the Laplacian. For example, Boaz Nadler proposed something which looks like this. Andrew Stewart kind of added the gamma to higher powers. And then there are questions how to apply them numerically. I'm not getting into this right now. I'm just writing L, where my idea is that if I need to use something higher than L, yeah, we know how to use it. It requires more work. It's a little bit more complicated. but measuring smoothness on a graph may require more than just graph Laplacian. It may require something with a little bit higher power. Okay. So again, many computational issues, I'm not going to discuss them here, but they exist in the literature, and they're not changing the fundamental ideas that I'm talking about over here. Okay, so here is estimating the labels. This is a really simple example that we cooked up. It's actually quite easy to do this. What you do is you go ahead and you label 2 points here as red. You measure 2 points everywhere else is blue. And when you apply this method, you get back this realization. Now, by the way, I've cooked here something specific that works. You see that this blue point is here and the other one is here. If I would take these 2 points and I put them in one side, the method will just give me something else, will give me something that may be completely one-sided. You really have to capture some of the geometry in that particular thing, and we're going to discuss this a little bit later. Parameters here we chose by generalized cross-validation, which is another nice thing when you do these kind of things. It's a linear problem. But you can see that even with very few points, you can label almost everything right. And that's kind of the nice thing about it. Okay, so assuming we know everything we need to know about semi-supervised learning, we can work to active learning. So in the semi-supervised learning, we looked at this example and we say somebody recorded these data. Somebody says to me, this is blue, this is blue, this is red, find the rest of it. Now I'm coming to this data clean, I have nothing, or maybe I have something, but recorded for me randomly. And now somebody says, where do you want to record this to get better estimate? So how do you get better estimate here? And that's where the semi-supervised learning becomes an active learning. So we're going to choose point where we want to sample. Well, the guiding principle is that we want to get a better estimate, because if we get a better estimate, we can train better neural network on it. Okay, so here is the most complicated mathy thing I have over here almost. You say, how do you estimate the error in your solution? So remember that this y was assumed to be polluted with noise, so we can't talk about errors as a deterministic thing. We have to talk about some expected value. So we take the expected value between y and y hat. So all these lines of algebra are, by the way, straightforward and known in other places. I stole them from previous papers about 10 years ago. What you do is you substitute, instead of y hat, the analytic expression that we had before. And then you kind of open brackets, you do a plus L and minus L to make life simple, and you realize that you can you can divide this thing into two things, like any other estimate in the world, into bias and variance. So the bias looks like this. So the bias square looks like this. The bias is what's inside the bracket here. And the variance is whatever happens here, where this capital sigma is the standard deviation covariance of the noise. If we assume that the noise is, the covariance is diagonal, then this becomes just a scalar, okay? And H is basically the matrix that I need to invert. So that's what I have here. So bias and variance, okay? And this is the error. Now, you can look, I'll say it in a second again, but you'll see that the error really that depends on two things. Depends on the variance that has nothing to do with the solution. So the variance does not really care what y is at all. I don't care what y is. And on the other hand, the bias really cares about what the true solution is. And remember, I don't know what the true solution is. This is where the issue really starts. So again, the variance does not depend on the solution. So it just depends on the noise. On the other hand, the bias depends on the solution. So if I want to estimate the error, I need to make some assumptions about the solution. There is no way I can say what the error is without knowing what this thing is, what the bias really is. And it turns out to be that for ill-posed problems, which is what we're solving over here, so a problem with not enough equations and too much data, this is usually the biggest contribution to the error. This one is usually a much smaller contribution to the error, what we've seen here. Okay, so let's talk about two ways to do things. If your religion is Bayesian, so if you believe that you can assume some stochastic properties of this variable y, you can go ahead and insert it into your equation and now start working with it. So for example, if you assume that y is normal with a zero mean and covariance matrix, which looks like the pseudo inverse of L, then you do a little bit of linear algebra, not very complicated, and you find out that the expected value over both epsilon and y, because again, y was stochastic right now, is just a trace of H inverse, which is a really nice expression. It's really simple and really nice. And it does not depend on y at all, okay? So this is called the Bayesian design, okay? And Did I skip one? No. Here. So again, we took this big expression, and we got back after we go ahead and we assume that that y is stochastic, and we say let's do an expectation over this, and we got that this is the expression we have to have. Okay, so we go ahead and say, okay, now what do we do? Well, this is a function of w, the weights. Now remember, if w is equal to 0, then I don't measure anything. If w is equal to 1, then I measure this thing. So w really encodes the labeling process. If it's not 0, I measure something. If it's 0, means I don't need that measurements. So until now, in the previous work of semi-supervised learning, we assume that this is fixed. Okay. Now I say, wait a minute, you can choose it any way you want. So you can choose w to have optimal recovery. So how should I choose it? Well, it's kind of obvious. If you choose it to be very large, then you label all the data, and of course, everything is right and there's no problem. But that, of course, defeats the purpose. I mean, I don't want to measure everywhere. I want to measure only a few places. So one of the things to do is to penalize non-sparse W. You want only a few of them and to give you the right accuracy. So the optimization problem you want to solve is this one. We're kind of fine. That's the final optimization problem we want to solve. We want us to minimize the trace of this guy, which tells us how what we're minimizing the error in our prediction. Plus the sum of these guys. You remember they're positive, so it's the same as saying that that these guys are looking at L1 norm of this. L1 norm will give you some sparse solution of these W's. And this is, by the way, an example for something like this that you get. If you do these kind of things, you get these kind of measurements. And I could end in principle the talk over here, but the story will not be complete because there is an issue with this. So again, if you're a Bayesian and you think that this is your solution, it's great. But remember that so far, this depends only on the graph Laplacian. It doesn't depend at all on anything else about what I labeled. So maybe I did a few labels before. It doesn't really change anything. If I label now, let's say I label the things based on what I found here, I'm still not changing the way I measure. There is no impact on whatever the true solution is to whatever I measure here, which is an issue here. It's a big issue when you're thinking about the Bayesian approach. So the Bayesian approach, it kind of, unfortunately, like our political process, you can think that you have a political belief, you go with that thing, you sample the world, and it doesn't matter what the details are coming back to you, you stay with your political belief. I'm not saying, because we're recorded, who especially have these kind of political beliefs, but this is really what this represents. You have a prior, the reality comes and hits you, but you don't care. You stay with the same ideas that you had before. And this is the problem with the Bayesian design. It depends on the prior, and it doesn't update the prior here. So you can do this. And again, I mean, you can start thinking, for example, and it's going to be useful for us because maybe when I do nothing, when I have no information, I can start by doing this. And you can say, as I sample more, I get my error to be smaller, and you can do these kind of gains. Okay. Now, again, I don't want to ignore, let's say that I did some Bayesian design to start with, and I collected some of the data, and I estimated my y-hat. Now, again, I mean, the problem with the Bayesian design, it doesn't really use the y-hat anymore. I can't really use it. I assume that y-hat comes from a certain distribution, and that's basically all I did. I'm ignoring whatever I came with. So there is no really advantage to what we call the active part. So I can't really measure some of it and come to the next thing. And I need to look at the problem a little bit differently. So going back to the drawing table and looking at the optimization problem, this is the optimization problem we started with without making any assumption on the true y that I don't know. Now, you can say, let's assume that I measured something and I came back with a y-hat here. So my students don't never know who is the Baron Minkhausen. I'm not sure how many people here knows him. The guy who lifted himself with his shoelaces out the hole. That's what we're going to do here. You can say, okay, we know why we did something. Doesn't matter if it's Bayesian or random or something, and we estimated y-hat. Let's plug this y-hat over here as an estimate, and now do a re-estimate of what we're doing and get a new y-hat and do the same thing over here. Now, it's possible to show that if you actually estimate the y-hat and plug it back here, this bias term is smaller than the true bias, which is kind of, if you think about it this way, if you're trying to find a smooth solution, you will find a smooth solution, even if the solution is not smooth, which basically means this is going to be smaller than this. So plugging this inside here gives you an idea. It's not the right thing to do because, again, you want the true y, but it gives you something reasonable. So what we're going to do is we're going to do this. We're going to solve a sequence of problems where we're going to every time plug a y hat in here and also calm down the regularization. So in a sense, you're measuring a few points, you're getting an estimate, you're plugging the estimate back, and you're getting the new points based on what you've seen previously and trying to increase the number of points. That's basically the algorithm we're taking. Okay, so here is a simple example. So if I have a test problem where this is my data, it's going to be, again, in 2 dimensions, and I can sample it. And I didn't try to do a movie for the whole sampling. I couldn't find the movies that we had on something like this. If you just randomly go ahead and sample, you get this curve. And if, on the other hand, you do the active learning, initially you do something a little bit worse, and then something a little bit, then you get something much better. I'll talk in a second about this initial phase, because that initial phase is actually important. So I'll say something about it in a second, of what happened in the beginning. So here is maybe we try to get intuition and maybe talk a little bit about what we're doing here. So here's our problem. What we do is we plug whatever we found the solution in the previous iteration in our bias term, and now we minimize this particular sense of equations. And if you look at the contribution, if you actually go ahead and you look at the numbers, what's the contribution of the variance versus the bias, you'll find out that most of the time we have found the largest contribution is coming from the bias. So what you can think about it is this way. You can say, let's solve the problem, find out where this is not very smooth over here, and at that point where the curvature is high, I want to add more data points. This is very similar, by the way, approach to what we do when we're doing adaptive mesh refinement in PDEs or ODEs. We solve the problem, we find out where gradients are very large, where things are changing very quickly, and then we add more points in the discretization over there. And this is exactly what this thing is telling you. It's telling you when you see that this thing is big, add more points in that area over here. That's the intuition that at least I have looking at this process. Okay. Let's talk about the last step. So far we just labeled the data. Now I can go ahead and say, okay, label the data. Let's go ahead and minimize over theta some parameters. You can add regularization for the theta, but I'm not writing it here. Where you're saying let's minimize over, for example, a deep learning, some loss between some trained model we want to do and the y hat. Okay, you can do it with least squares or anything else. Now, the reason I want to show least squares is because there is an unresolved issue here that maybe Mark can tell us if this is really resolved in the literature. So what happened here, that least squares is not really the right metric over here because the y hat are correlated. When we did the process that estimated all the y hats, clearly we looked at smoothness, which means that if something close by to it is one label, it should be something else is there as well, which means that the errors are now correlated in the y hat. And therefore, you should really look at loss that looks like something with the covariance matrix in there. And now comes the real question. I mean, how do you go ahead and you minimize something like this with, for example, like SGD? Because SGD does not assume covariance as much as I know. And using covariance in the SGD process is not easy. So there is questions about how to do this. What we did, we did some diagonal estimation of these things, but as much as I know, this is not a fully resolved problem for these kind of things. So this introduction of non-trivial covariance between data points is not an easy thing to deal with when you want to do it right. You can do stuff always, you can just ignore it. But the right thing to do is to somehow treat it, and that's not necessarily a simple thing. So let's look at examples that people have looked in the literature as well. So, for example, let's look at MNIST. Here, what we call AL5, we add 5 points every time we do an iteration, and we compare our thing to just a random things. And again, in the beginning, the random is doing a little bit better, and then we win. The most interesting thing to remember about this thing, and this is, I think, one of the kind of take-home messages I have for myself, is that all these algorithms we're doing are based on the fact, I mean, if I go back for a second to here, they're based on the fact that this y hat has a meaning. So again, I go to what I understand maybe a little bit better is adaptive mesh refinement in ODEs or PDEs. If you decide, let's say, to add points, because that's really the equivalent thing, is adding points to a solution of a PDE or an ODE based on the previous solution we have. So you can think about it this way. If you decide to solve a Poisson equation with 3 points only, you're so far away from the true solution. that whatever you're doing is meaningless. And then just random picking of points will be better than you picking a solution based on the previous set of points. Now we're in much higher dimensions. So how many points are actually needed until this y hat represents somehow the true solution? If you have too few points and you're making decisions based on this y hat, then you get exactly this curve. You get that just doing random numbers, a random set of points, is doing better than choosing the thing here. So recent work we've done, for example, we look at what we call exploration versus exploitation. I would say that what we're doing in this work, which I've not shown you the exploration part, we're doing exploitation. We're just getting the model and we're exploiting it. You can think about combining and adding random to the thing until you see things are stabilizing, and now you're saying, well, it's time for me to avoid just exploring the space and let's just exploit the space. So again, this is just for MNIST. If we compare the work we have done with other work we've seen around, there is not a lot of work. So this is work which was done in 2017, when they actually counted how many examples they need to get to 10% accuracy into 5% accuracy, and their numbers depends how you want to do this only supervised learning, and this is their numbers. So they need 128, 255 for random, 295 and 835 for random. So this is much better than random. When we do our trick, when we first do the estimation of everything with semi-supervised and then do the training, we get to much less than what they do as well. Graphically speaking, this is another paper that came by Nowak. This is not, none of them is really our results. These are all his results. And you look at on MNIST, he is worse than 10% accuracy. And we started ours in better, like if you look at, again, with 38 examples, we're at 10%. They are very, very far for 10%, even when they go to 500 examples. So, you know, not even pointing this on the graph here. This idea that you don't label the data first, but you start the machine learning without labeling all the data seems to be hurting them in this particular case. Okay, so I promised 45 minutes, and it's 45 minutes. So here is a quick summary. So first thing, optimal experimental design exists for many, many years. Active learning, of course, is machine learning, so it has to be sexy. So it's a sexier implementation or a cousin of a sensor placement problem or optimal experimental design. What we decided to do is to separate the labeling and the training phases. We don't want to do them at the same time. It allows us to, treat the problem a little bit more, see each problem a little bit by itself, which there is theory for at least one of them, very well-developed theory. And the second thing is we can also compose different methods when you are practical. This is the A optimal experimental design. There are others. There is a whole host of techniques for those of you who are interested. There is A, there is E, there is F. I mean, there is a lot of different techniques out there. Optimal is probably the most common one. It just looks at the error in a very simple way. And there are only a few numerical examples right now. We worked a little bit on CFAR 10, but again, I mean, there is going to be more numerical methods on these things, and I did not talk much about the numerics in these things. This exists in other papers, but there is quite a lot of numerics here. It's not as simple and as clean as it looks like. There is quite a lot of details to make this whole thing works. I think that's the time to finish.
Thanks, Eldad.
Thank you.
So you didn't disappoint. You apparently imply that all Trump supporters are Bayesians.
It's a strong fire. A strong fire.
I'm sure that there's some folks out there with questions. I'm going to suggest that you raise your hand, and then I'll call on you. So if there are any questions, oh, what happened to raised hands? Seems to have disappeared. Oh, no, there it is. Okay, maybe I can't raise my own hand. So Michael Gu, why don't you go ahead?
Yeah. Hello, Professor. First of all, thank you very much for the presentation. I would just like to ask a question. I know the numerical experiments for this method is done on MNIST, which is kind of like a simpler data set that you can solve with models with lower parameters. I'm asking for this kind of model, what is the challenge in the scalability? Is it with the dimensionality of the data, or is it with the number of classes, or anything else?
So there are two problems. First thing, the graph Laplacian. is not easy when it depends on the number of data, right? So this is a good question about what happens. So right now, we started a project with IBM where they're looking at doing it for actually at infected versus not infected over the whole US population. So the claim was that, 330 million, like a graph of 330 million is not really such a big graph. They can use it. But when you try to do it on your laptop, let's say, this is not so easy. So everything that relates to, that scales up as the data size is not trivial to do. So I would say that a lot of the numerical techniques, like, I brushed very easily. And again, I'm sure there are some people here that I know they're here, and I'm kind of afraid that they'll ask this question, but here. So you look at this thing and you say L plus gamma I to the power of gamma. Take Laplace into the power of gamma. Who would ever do something like that? This is not an easy thing to do. And practically speaking, these kind of details can be very complicated to do efficiently and to deal with when you have a large set of data points. So I would say that's the most serious problem that I see here. The second thing is exactly like I said over here. I try to kind of be honest about this. This distance function works very well for MNIST. CFAR10, for example, this is not so great. Looking at least squares is not so great as a distance function, or L2 between two points. So finding the right D for a different data set, that's a challenging thing. And I'm not claiming I know the answer. And I think it's very much data driven or data dependent. And that's, to me, is a crucial point in making it work on large data and complicated data, not MNIST.
Yeah, I can imagine how difficult that is when your data is not, when you've got categorical data, for example.
Yeah. Oh, but again, one of the things that we have been working with some success is using autoencoders for these kind of things. So autoencoders in order to measure data difference. But this is not unique to us. To be honest, the whole process depends on the fact that semi-supervised learning, a graphical method for semi-supervised learning work. If you don't know how to do semi-supervised learning, the method cannot work. That's basically what we're trying to say here. So if you have if all techniques that using semi-supervised learning techniques don't work for you, you're screwed. That's what we're trying to say here.
Okay, I see a question in the chat from Betty Shea. How sensitive is the method to the initial samples picked? And are there any guarantees on the quality of the sequence picked? For example, benchmark to some best sequence in hindsight.
So I don't know if, I don't think there's any theory that will say that we can have a best sequence. It goes back, so first thing, it can be very unstable, very, very sensitive to the initial sequence. It goes to this idea of exploration versus exploitation. So again, the whole point is that I need to estimate this Y somehow. So if I, by chance, let's say that I start with running 100 points randomly, and this 100 points randomly are doing a good job in estimate, so this Y hat is a good estimate of this Y, then the method will fly. You'll get really, really good things. If on the other hand, I choose 100 points, and by luck, these points are really, really bad, they're just not giving me anything really good, then things can go very wrong, because these points would lead you to the wrong place, and it will take you time to correct them. Now, there are guarantees for the Bayesian design, but you have to realize that these guarantees are happening only in expectation, and only when you assume that you have the right probability density function, which none of them is really important, because we never have the right probability density function, and guarantees in expectation are not really interesting in some way. They're kind of interesting, but it doesn't really mean that it's going to work for you. So if you want theory, then go to the Bayesian. The Bayesian really are good in theory, but the Bayesian assumptions are extremely strong. Knowing that this Y is coming from a probability density function, and knowing what the probability density function, that's a very, very strong assumption. So realistically speaking, the answer is no. What we typically see is exactly the behavior we showed here. And again, we actually try to show it in different places, is that in random, you can get better results initially if you do things random, because your Y hat is probably not accurate enough. And as your Y hat becomes accurate enough, you're going to get better results. And by the way, this should not come as a surprise. Anybody who, for example, tried to use adaptive methods for partial differential equations have seen that if you just have too few points, then doing something on a random, or doing some kind of pre-design equidistance or something works relatively well. And only when you start estimating the solution correctly, then you actually can get gains from, using the solution you just estimated in order to get the next points.
Okay, if anybody else has a question, please raise your hand. I will ask a question in the meantime. I didn't quite follow the Bayesian analysis. You assumed partway through that your y was being drawn from something simple, like a normal distribution. Are your conclusions about the fact that your optimization no longer depends on your actual samples, do those still hold if you assume some other form of prior?
So it doesn't matter what prior. I mean, the point is, maybe I did not make myself clear. This is a really important point here. So what you do here is this. It doesn't matter for a second what distribution, because I do an expectation over the y, correct? That's the reason I get something independent of y. So the Bayesian design says something like this. I mean, you don't know what this y is, so why don't you just do an expectation over it? And if you know what the distribution is, then do an expectation. Now, because it's Gaussian, then it's very easy to get an analytic expression. If this would be something crazy, then I can do an expectation, but it would not be anymore. I have to do Monte Carlo or something more sophisticated. But the thing is that it's never going to be dependent on y. It is the A design, never going to be dependent on y, because you are averaging over y. So again, I mean, it depends of how do you want to view this. Do you want to average over y? By the way, I did not talk about min-max, which is another approach. The paper by Nowak is really closer to min-max. You can say, let's try to look at the worst case of y. So let's try to maximize over y and minimize over my w. I did not really do, in the experimental design, people do this. So if you were designing a plane, you can say, let's assume the worst case scenario is actually happening to me. Typically, that will be one way. And then, of course, you do depend on the y. But the Bayesian approach is usually saying, let's average over the y, assuming that I know something about the distribution of it. That's a typical.
Right, and then the distribution doesn't actually matter, because the results become independent of the samples.
Yes, so the distribution of the y matters. Whatever you got back it doesn't matter, because it's just one realization out of the infinite models that exist out there that come from the same distribution. That's really the thing. Okay,
thank you. I am not seeing any more questions, and we are coming up on 4 o'clock. So Aaron asked me to mention that next week at 2 p.m., so an hour earlier than today, CAIDA has another talk by Kyung-Yun Cho from New York University, titled "The Inconsistency of a Recurrent Language Model, a question I forgot to ask in 2014. So I'm sure we'd love to see you at that talk next week. And let's give another round of applause for Eldad's talk today. Thanks very much, Eldad.
Thank you for everyone for showing up.
Great. Thanks for coming, everyone.
Okay.
Okay. Bye-bye.